How to charge LFP batteries on a boat. Part 1. Curve explanation. Single cell charging. In this video, we will look at a charge-discharge curve of an LFP cell, based on which any lithium iron phosphate battery is built. We will charge and discharge the new cell, following the manufacturer's recommendations. We will find out its real capacity. We'll look at the curve. Based on the curve, we will highlight the features of the constructive chemistry of LFP cells. We will charge the cell with an ultra-low current of 0.1 C to a voltage of 3.45 volts, simulating real operating conditions from a current point of view on a boat for most users of alternative energy. Let's see if 3.45 volts per cell is enough for getting a nominal capacity. Then we will charge the cell with a low current of 0.2 C to a voltage of 3.45 volts, simulating real operating conditions on a boat for users with a developed charging resource. We'll see the result. Then let's find out what fast charging is and the features of this mode. Let's talk about the prospects for fast charging LFP. How fast you can charge LFP in reality with an unlimited charging resource. Let's find out the effect of charging conditions on the increase in cell temperature. And summarize. Welcome to the Channel Paradise Workshop. Please note that in this video, we are talking about typical LFP cells with working ends of 2.5 to 3.65 volts. For iron phosphate cells with yttrium and with working ends of 2.8 to 3.8 volts, for example, Winston battery, the curves are different. It is also not recommended to discharge these cells to 2.5 volts. For tests, we will take an LiFePO4 LFP cell. The capacity rating of 20 amp-hours will allow us to conduct tests with a current of up to 1 C. Let's measure alternating current internal resistance. Okay, it's 1.63 milliohm, which corresponds to the manufacturer's passport values. The ambient temperature is 31 to 32 degrees Celsius, which corresponds to the average temperature of boat use in tropics and subtropics in summer. In this video, we will talk about the next current. 0.1 C, 0.2 C, 0.5 C, and 1 C. To determine exactly what current will be in your case, just multiply the total capacity of your batteries by the current value from the video. For example, for a capacity of 800 ampere-hours 12 volts, we will get the next values. First, we need to charge and discharge the new cell according to the manufacturer's recommendation. For our cell, the standard charge means charging the cell at a constant current of 10 amps until the voltage is 3.65 volts, then charging at a constant voltage of 3.65 volts until its current is less than 1 ampere. The standard discharge means discharging the cell at a constant current of 10 amps until the voltage is 2.5 volts. So let's go. We charged the new cell to 3.65 volts and then discharged it to the manufacturer's stated value of 2.5 volts. We found out that the actual cell capacity is even more than what the manufacturer claims. Before we move on to testing the different modes and explaining them, we wanted to note one important point. After charging stops, the voltage gradually drops to the rest of the voltage point and even lower. The rest of voltage point for LFP is approximately 3.37 volts. We charged our cell with a current of 0.5 C to 3.65 volts with an absorption below the current of 0.05 C. On the curve, we see the main two stages of a modern smart charger. The first stage, bulk, or constant current, is the stage when charging occurs to the required voltage value with a constant or maximum current for the source. The second stage is absorption or constant voltage. At this stage, the charger maintains a constant voltage, and the current gradually drops to the required current value or continues for a certain time specified by a user. Absorption is an important element for balancing the cells combined into a battery, which we will talk about in more detail in the following videos. Important points about the charge curve. After a complete discharge to 2.5 volts, after turning off the charger, the cell voltage will slowly rise. The LFP curve, except for the lower and upper knees, is extremely flat. There may be several segments in which the capacitance will increase, but the voltage will not. Depending on the charging current, one voltage value can correspond to different cell capacities. That is why it is impossible to determine the exact value of a stage of charge by voltage. When charging with a current of 0.5 C on the upper knee of the curve, the temperature of the open cell in the laboratory rises from 32 to 37 degrees. Cells in a closed marine case show a higher result, which makes us think about a possible reduction in time in this mode to avoid degradation. Charging in this mode took 2 hours and 5 minutes, of which only 5 minutes of absorption mode. Okay, we learned about the standard charging mode with a current of 0.5 C. We also saw an active increase in temperature which, under our operating conditions of cells at high ambient temperature and in sealed marine cases, is likely to lead to degradation and a decrease in the lifespan of the cells. Let's test the cell's operation with lower currents of 0.1 C and 0.2 C, close to boat charging currents, and lower the target voltage to reduce the cell's operating temperature. We will see how it performs. Okay, we charge the cell to 3.45 volts with a current of 0.1 C. This is the current that is often used to charge batteries on boats from alternative energy sources. For example, we use solar panels in our mobile laboratory. For our 800 amp-hour LFP test bank, for example, this current equals 80 amps. We got approximately the same capacity when charging up to 3.45 volts with a current of 0.1 C and absorption of less than 0.05 C. The temperature of the cell rises by 1 degree. Total charging time is 10 hours 12 minutes. The duration of the absorption stage is 3 minutes. For cruisers who have more developed charging sources and fully charge their battery bank during daylight hours, the next mode will be more interesting. Charge up to 3.45 volts with a current of 0.2 C with an absorption of less than 0.05 C. This mode will be of interest to those who charge batteries in parallel from several current sources, for example, solar panels and an alternator or a shore charger. Let's see how the cell performs. We charged and got approximately the same full capacity of the cell. The temperature rose by 3 degrees. The charging process took 5 hours and 12 minutes and the absorption stage about 14 minutes. Let's compare all three modes. If charging up to 3.65 volts with a current of 0.5 C, we were able to get a maximum capacity of 20.56 amp-hours. If charging up to 3.45 volts with different currents, an average capacity is 20.4 amp-hours. The difference in capacity is only 0.78%, while we lowered the cell temperature, which was important for us. Charging lasted 2, 5, and 10 hours. Based on this, mode constant current plus constant voltage 3.45 volts can be recommended as optimal for everyday charging at high temperature ambient conditions. Okay, what about discharge? The curve also changes depending on the discharge current. Let's look at two discharge scenarios. Cruisers on boats mostly use the first one. Discharge current not exceeding 0.1 C. In this case, the voltage of 3.17 equals 10% of the state of charge. Discharging the cell below 10% daily is not recommended for long cell life. The lower discharge threshold of 20% is perhaps optimal. The second discharge scenario with a current of 0.5 C is usually used by powerful consumers, such as a dinghy electric motor. In this case, the voltage of 3.17 corresponds to the state of charge of 23%. You can easily imagine how the discharge curves will change in case of a current less than 0.5 C but more than 0.1 C. The curve will be located between them. This once again confirms that it is impossible to determine the SOC of a battery by voltage alone. Fast charging of LFP cells. How fast can we charge standard DIY cells, and what are the limitations? Typically, fast charging is charging with a current of 1 C or higher, depending on the cell. You need to know that fast charging shortens the life of the cell, but there are cases where a fast charging scenario is necessary. Two fast charging options on the screen. The first one is up to 3.65 volts and the second one is up to 3.46 volts. The constant voltage 3.46 mode was chosen as a method to simulate a current drop at the SOC level of 75 to 80% since many manufacturers do not recommend using the 1C charging mode above 80% SOC. The full charge to 3.65 volts lasts a little over an hour, while the cell temperature rises to 43 degrees Celsius. The full charge to 3.46 volts lasts about an hour and a half, and the temperature rises to 39 degrees. Full fast charging, in our opinion, is meaningless, as it either significantly increases the temperature of the cell or, taking into account absorption, lasts quite a long time. For full charging, it is better to choose a method with a standard current of 0.5 C, which lasts 30 minutes longer, but the temperature is lower. But fast charging makes sense when you need to partially recharge very quickly. For example, in the case of an emergency or the case of quick charging of an electric motor of a dinghy and other similar options. In this case, fast charging, from 10 to 70% state of charge, for example, will take less than 40 minutes. In this case, you may not specifically change the program of your chargers, but simply turn on all available chargers, if all of them together are capable of delivering such a current. But still, in our opinion, for 12-volt systems, and most of them are on boats, this is more of a theoretical possibility than a real scenario, because the 1C current even for medium-sized battery banks of 800 amp-hours is 800 amperes. And this is a very high current. Now you know more about LFP cells. In future videos, we'll dive even deeper and talk about combining these cells into battery banks and how sometimes running in series mode, as well as running as part of the actual infrastructure on the boat, makes adjustments to the charging parameters settings. Subscribe to the channel. Thank you, and goodbye.